The universe is awash in waves. We see some as light, feel others as heat. But there's a hidden realm, a swath of the electromagnetic spectrum we're only beginning to explore. Terahertz radiation. This band of frequencies, nestled between microwaves and infrared light, holds immense potential for medicine, communication, and beyond. But to unlock its secrets, we need tools capable of manipulating these terahertz waves. Enter metamaterials. Metamaterials are not your typical materials. They are engineered, often composed of repeating patterns of metallic structures, meticulously designed at a scale smaller than the wavelength of the radiation they manipulate. Imagine a symphony orchestra, each instrument tuned to resonate with a specific frequency. Metamaterials are like crafting entirely new instruments, each designed to resonate with and control terahertz waves in extraordinary ways. These engineered structures, these meta-atoms, interact with the electric and magnetic components of terahertz waves, giving us unprecedented control over their behavior. We can bend them, focus them, and even absorb them, opening up a universe of possibilities. We stand on the precipice of a technological revolution, fueled by our growing mastery over the terahertz realm. Just as the telescope unveiled the cosmos, Terahertz Metamaterials promise to unlock new frontiers in science and technology. Prepare to have your perception of the universe expanded. Imagine a stone dropped in a pond, ripples spreading outward. That's how electromagnetic waves, including terahertz waves, propagate. These waves have both electric and magnetic fields, oscillating perpendicular to each other. Metamaterials, with their intricate structures, can interact with these fields, shaping the very fabric of terahertz radiation. One of the simplest yet most versatile metamaterial building blocks is the split-ring resonator, or SRR. Picture a tiny metallic square with a gap, like a miniature racetrack. When terahertz waves hit this SRR, the electric field induces currents within the metal. These currents, in turn, generate their own electromagnetic fields, interfering with the incoming terahertz waves. The shape of the SRR, the size of the gap, even the material it's made of, all these factors influence how it resonates with terahertz waves. It's like adjusting the tension of a string on a guitar, changing the note it produces. By carefully designing these SRRs, we can create metamaterials that selectively absorb, reflect, or transmit terahertz radiation at specific frequencies. But the story doesn't end there. The orientation of the SRRs relative to the incoming terahertz waves also plays a crucial role. Just as a polarized sunglass lens only allows light waves oscillating in a specific direction to pass through, changing the orientation of SRRs can drastically alter their interaction with the polarization of terahertz waves. This control over polarization opens up exciting possibilities for applications in imaging and sensing. In the vast expanse of the electromagnetic spectrum, from the gentle hum of radio waves to the high-energy bursts of gamma rays, magnetism and electricity are forever intertwined, locked in an intricate dance. At terahertz frequencies, this dance takes on a new significance, one we can manipulate with the help of metamaterials. While individual split-ring resonators, or SRRs, primarily interact with the electric field of terahertz waves, we can engineer them to exhibit a magnetic response as well. Imagine two SRRs nestled close together, their gaps facing each other. This configuration, known as a double SRR, exhibits a magnetic dipole moment when excited by terahertz radiation. It's like creating a tiny magnet, but one that only turns on in the presence of specific terahertz frequencies. By stacking these double SRRs in multiple layers, we can further enhance this magnetic response, amplifying the interaction between the metamaterial and the terahertz waves. But how do we excite these magnetic responses? Unlike conventional materials, where magnetic properties arise from the inherent spin of electrons, in metamaterials, it's the collective motion of electrons induced by the terahertz radiation that gives rise to magnetism. This unique characteristic allows us to create materials with tailored magnetic properties, something unimaginable with naturally occurring materials. The ability to engineer both electric and magnetic responses in metamaterials opens up a world of possibilities. It's like having a set of building blocks, each with its own unique electromagnetic properties, allowing us to construct materials with unprecedented control over terahertz waves. We take for granted that light travels in straight lines. It's the foundation of our visual perception, the reason we see shadows and reflections. But in the realm of metamaterials, the rules of the game can be bent, literally. Prepare to enter a world where light can be coaxed to flow backward, a phenomenon known as negative refraction. Imagine a straw submerged in a glass of water. From the side, the straw appears bent at the water's surface. This illusion occurs because light refracts or changes direction as it passes from one medium to another. Normally, this bending follows Snell's law, dictating that light bends towards the perpendicular when entering a denser medium. However, metamaterials can be engineered to have a negative refractive index, meaning light bends in the opposite direction, away from the perpendicular. This counterintuitive behavior arises from the unique interaction between the metamaterial structure and the electric and magnetic components of the electromagnetic wave. Structures like planar SRRs, with their ability to manipulate both electric and magnetic fields, can be arranged to achieve negative refraction. Other designs, such as metallic crossbars, S-strings, and even chiral metamaterials, which exhibit a handedness like a spiral staircase, can also exhibit this remarkable property. Negative refraction has profound implications for optics and beyond. Imagine lenses that can focus light to a point smaller than its wavelength, breaking the diffraction limit that has long constrained optical microscopy, or cloaking devices, capable of bending light around an object, rendering it invisible. The possibilities, once confined to the realm of science fiction, are now within the grasp of metamaterial research.